even in the best quality samples, is that as you cool down from, say, 4 Kelvin to 30 millikelvin, the energy versus momentum, SSU and omega, that you get from inelastic neutron scattering doesn't really change all that much. So you have this kind of broad continuum-like scattering, which is, this would be in the paramagnetic state, doesn't seem to really be modified by this transition very much at all, and certainly you don't see any sharp spin wave excitations that you would expect from an ordered ferromagnet. In addition, in this single crystal, what we see is a large amount of diffuse scattering. Here I'm isolating it. It's actually quasi-elastic in nature, so I'm isolating from 0.1 to 0.3 millielectron volts just to show it better. But what happens as you go through the transition here is you don't lose this diffuse scattering, and instead you start to see it build up closer to the 111 Bragg peak, almost as if it was trying to become a long-range ordered state, but doesn't quite make it there. So in this single crystal, we do not see any signs for a long-range ordered ferromagnetic state. But one thing that we could do, and this ended up being extremely useful, is that we can apply a magnetic field to the single crystal samples and then measure the inelastic excitations as a function of field. And as you see here, if you apply a small field of 0.25 Tesla, you start to lift up this diffuse scattering, and it starts to organize itself into these sharp spin waves. This is a signature that we're entering a field polarized state. And if you go to high enough fields, you can imagine that this could be well described by a linear spin wave theory, which is what we did. So working with Leon Valence and Lucille Fabry, we were able to fit our data to this anisotropic exchange model. And you can see here we did this for 2 field strengths. And let me point out that the field was along one direction, 1 bar 0. And we chose this G-tensor in order to model the spin waves with. This was actually extracted from a crystal electric field calculation. And so doing this, we came up with a nice comparison with the 5 Tesla and 2 Tesla data, and we're able to robustly conclude that we have these 4 exchange parameters, the largest one being this JZZ, which, as you see here, is the largest and is ferromagnetic, which is, in fact, what you'd expect for a spin ice. So if these other terms were not present, you could say that you had a classical spin ice. So you might expect to have monopoles arising from spin flips in that type of scenario. Now, these other exchange parameters, which are smaller, but as you see here, not tiny, right? So this is the same order of magnitude. These could potentially be thought of as introducing quantum fluctuations into a spin ice model. And from that, you would have not just the monopoles, but you'd have emergent electrodynamics. So you'd also have emergent photons and emergent electrons, which would be extremely exciting. So if you take those parameters and try to understand what the ground state is, this was done by Leon and Lucille, and they did this using something called gauge beam field theory. What they found is that for large JZZ, there's 4 phases in the phase diagram, 2 of which are exotic. One of them is the quantum spin liquid, which supports this emergent electrodynamics with the photons, monopoles, and electrons. And then there's another interesting phase here, the Coulomb ferromagnet, which is a partially polarized phase that's related to this quantum spin liquid. So it has the same quasi-particle excitation, but it has a partially ordered moment. And then these other 2 phases are more conventionally ordered phases of ferromagnet and an anti-ferromagnet. And so, depending on where exactly these phase boundaries are, keep in mind this is the type of mean field theory, so that these could be shifted around a little bit. You could think that ytterbium titanate might be close to some of these phase boundaries, which may explain why it's so sensitive to disorder. Furthermore, recently there's been some very nice work by two other groups who have come up with another alternative set of parameters, actually two different sets of parameters, but they're close to one another, which indicates that a terbium titanate may lie close to a classical phase boundary between the displayed ferromagnetic state and these two antiferromagnetic phases, psi 2 and psi 3. And so in this scenario, this would also be a case in which we're lying close to a phase boundary and having the influence of perhaps strong quantum fluctuations because of that lying close to that boundary. And so one question is, what role does the known sample dependence play in where we are in these various phase diagrams? So let me focus on two of the powders, or two of the terbium titanate samples that were made at McMaster University. One of them is the single crystal that I've been telling you about. This was grown by the floating zone method. And the other is a powder sample, which was never grown as a single crystal. So this was purely solid state, never been melted. And as you can see here, this is a log scale